Okay, welcome to lecture. We'll get started in just a bit here. We should be on to chapter 15 as we finished up chapter 14 last time. So again, like usual, if you do have any questions, feel free to obviously ask them in the box below. And if we definitely get to your answer, again, if we've moved on, we'll go back and answer them. So again, we finished chapter 14, titrations, indicators, last time, I think during lab. And then, so we're off to our next one here, which is chapter 15. All right, so let us, there was, yes, so we lectured and then we talked about the experiment. I'm not sure, did you go through the lab one? So that's where we did it. Yeah, so there was a lecture last time during lab. I'm not sure what happened. It was a little choppy, if you remember last time. So we took a break. You guys were working on the example, and then we went through the example there in lab. So really the lab lecture sort of consisted of that last example that was in the notes in chapter 14. So if you weren't able for some reason to get in, make sure you go watch the recording, which should be up pretty soon. If it's not up there already, it might be. Yeah, it was originally going to be due today. I think the project proposal, I think, extend it to like Sunday, I think, or whatever it is, just to give you a couple extra days or so if you need to kind of organize and get it submitted. So you can submit the project proposal today, or again, I think I moved it just to give you, like I said, a few extra days by Sunday. Other questions on anything? Okay. So then let us get started here. So again, a reminder that we did have a lecture there in lab last time, and after that lecture, we also talked about the buffer experiment as well. So which is up and online as well. So if you for some reason didn't catch it, make sure you take a look at the recording for that information and stuff like that. So it was essentially the last example there in chapter 14, the titration problem. We talked a little bit about indicators as well. And then we talked about buffers and the buffer experiment too. So all that stuff is up in that lecture. So make sure that you take a look at it if you, again, missed it, or if you were there, if you need to look at it again, you can. And I think it should be up there. If not, I'll double check after today's lecture and all that to make sure it's up there on our Canvas site. All right, so chapter 15 here, we're going to continue our talk about more Ks, but we're going to get some different Ks to add to our ever-growing list of Ks, our Kc, or Kp, or Kw, or Ka, or Kb. So now we're going to talk about in this chapter sort of KSP and KF. KSP, as we'll talk about it, has to do with what is known as solubility product. That's what the SP stands for. KF is the formation constant, which we'll talk about towards the end of this chapter, which deals with complex ions that are formed. So let's get going with, first off, I think the KSP. So KSP, which is solubility equilibrium, and it really is a equilibrium constant that is written for things that are typically insoluble. So if you think about kind of our solubility rules that you know, when we think about things that are insoluble, we oftentimes think about it in the sense that they are always going to be solids, they'll never dissolve, and all those things. Now, it's important to realize that even though something is technically insoluble, there is always some degree of solubility with things that are still insoluble. It's obviously extremely small, which is why it's considered insoluble as sort of a whole. When we think about it, when we think about, say, silver chloride, like we see up there, based on our solubility rules, right? Chloride is soluble with everything except for silver, lead, and mercury. And in this case, it contains silver. And we normally think of it as making a solid. But again, things that are insoluble still have some degree of solubility. So what that means is even though this thing is technically a solid up here, it will in solution still break apart a little bit into these ions. So it still has the ability to form those ions in solution, and it actually will come to equilibrium between the solid and the ions that are in solution. Um, Not a lot of ions are going to come out, which means, as we'll see, the KSP values are typically relatively small for these guys, but there is some degree of solubility that occurs even with things that are technically insoluble. And we can write really an equilibrium constant for this guy here, where we do our products over our reactants. And in this case, it would be the silver ion, like we see, times the chloride ion. And just like normal, since our reactant side's a solid, that essentially is our equilibrium constant. And as you see to the left there, this is what is known as the KSP. So the KSP is the solubility product, and it is essentially an equilibrium constant for things that are typically thought of as being insoluble. And that's sort of an important aspect of KSP, because when you write these sort of equations, if you will, we have here, or any of these guys down here, it always goes this way. It's always the solid guy on the left, and it always goes to the aqueous ions on the right-hand side, positive guy or negative guy. And that means when we do typically write KSP expressions, it's really just the products that are involved. Again, because the reactants are typically solids, and as we talked about, the solids are not included in the equilibrium expression. So we do it the exact same way as we do any other equilibrium constant. Even though it's called a KSP, it is still just an equilibrium constant at heart. It is still products over reactants. The only difference is, as we again can see in these other examples down here, always, for the most part, on your reactant side, they're always going to be solid, which again means that our KSP expression will typically just be our products. We still, just like a normal equilibrium expression, we're still going to use the coefficients as our exponents. So again, that's important as well. So you can see again, because the 2's in front of that F minus, we will add it over there and use it as the exponent. Same thing with our silver and our carbonate. We have a 2 in front of the silver ion, so it would be the concentration of silver squared because of the coefficient times the concentration of carbonate. And our calcium phosphate, again, we have 2 coefficients. Again, they both end up in the KSP expression. So KSP, an equilibrium constant, essentially, an equilibrium constant pretty much used for things that are thought of as being insoluble. And when we write these reactions, again, on the reactant side, always are solids and go to our products. And when we do have something that's ionic that goes into solution, we do get a couple of different sort of options in terms of the type of solution that we could get. And we could use something else that we've also have seen before, and that is Q. So if you remember, Q is the reaction quotient. And remember that we calculate Q the same as K. So Q is also products over reactants. And if you remember, we use Q to determine usually whether or not a system is at equilibrium, right? And which way it needs to go to reach equilibrium. We could also use Q and KSP to help us decide what type of solution we have and whether or not we would expect a precipitate to be made. So if you calculate Q, which again would be calculated the exact same way as you would calculate your KSP, which means essentially you would take the concentration of the ions at equilibrium and put it into that expression of the products. And if Q is less than the KSP, again, you could kind of do the opposite of where that guy points. So if you put Q on the left and K on the right, and again, our reactions are always basically written this way, solids to aqueous ions. So if Q is less than KSP, we would expect it to go opposite, and we would expect aqueous ions to be formed, which means we would have an unsaturated solution and we would not expect any precipitate. An unsaturated solution, again, right, is a solution where if you take some solute, for example, some type of solid, it will continue to dissolve at that point because you have not hit really the saturation point. So solid will continue to dissolve. So one way we could predict if we take two solutions, like we'll look at a little bit later on in this chapter, we take two solutions and basically mix them together, we could predict whether or not we will get a precipitate to form. Now, if you calculate Q and it does equal the KSP value, then you have a saturated solution at that point. And a saturated solution is, as you hopefully know, is the point where you've hit exactly at that temperature, because solubility is based on temperature. You hit exactly at that temperature the maximum amount of solute that will dissolve in a solution. So you're right at exactly that point where everything will continue to dissolve. And you're also right at that point where it will then stop dissolving. Obviously, if you try to mix some more in there. So you're right at that, basically the end of its sort of solubility when you hit that saturation point, and you would have a saturated solution. If you calculate Q and it's greater than KSP, again, it would go kind of opposite of where that is pointing, which would take you to this side of the equation, which is the solid side. And if we calculate Q and it's greater than the KSP value, what that would tell us is we typically have a supersaturated solution. And typically in a supersaturated solution, you have too much solute to solve it. And usually the solid will come out of solution, and we would expect a precipitate to form in that case. So we could use Q, which again is basically calculated the exact same. So we would take our products, and in this case, none of our reactants because they're going to be solid. And we would compare it to the KSP value, which again, you could find either on a table or it would be in the problem. And you can determine whether or not something will make a precipitate or not. Now, what we'll see in this particular chapter is there's a lot of factors that affect solubility. So just because we think about things based on sort of their solubility rules, which again, if you're not familiar with, you might want to do a little bit of reviewing of those things. Again, like a lot of things, you'll be able to probably figure out what you need to know, but you know, if you've been a while since you maybe looked at a solubility sort of table or something like that, again, you may want to kind of review that to help you along here. So what we will see is even though based, say, on a solubility table that something should be insoluble and we should expect a solid to be formed, there are a lot of factors. There's things like concentration of the ions that are important. There's things like pH that's important. There's things like common ion that's important in terms of, you know, whether or not you'll actually see that solid. So you could have something on the solubility table, for example, say our silver chloride here, for example, and you know, you think, hey, I'm going to always get a solid no matter what happens when I mix silver and chloride together. And that may not always be the case, especially if you don't have perhaps the right concentration of those ions to actually be able to see the solid. You may not actually see a solid, even though technically speaking, based on the solubility rules, you're supposed to always see a solid. There's a lot of factors, as we'll talk about in this chapter, things like I mentioned, solubility, pH, that do affect whether or not perhaps, even though technically speaking, you should see a solid, if you will actually see a solid in that case. Any questions on that? So here's a table badly cut and pasted into here, but this is from your book. So again, you may have to reference, obviously, this table for certain problems. They may not necessarily give you the KSP value. But what you will see when you look at this table, or if you're looking at this table here, the thing that you will typically see when you look at a KSP type of value is the KSP value are usually very small. So these KSPs, if you look here, that's extremely small. A lot of these exponents, as we look at them for each of them, are really small values. And again, because these things are really still equilibrium constants, it means the same thing, that when we think about a reaction, we have our reactants that go to our products. If we have a very small equilibrium constant, which is our KSP, when we reach equilibrium, we should mainly have reactants. And since all these reactions are solids that go to ions or aqueous guys, that means that typically when we reach equilibrium, we do mainly have the solid there still together. But again, even things that are insoluble will have some degree of solubility, even if it's super small. Something can still break apart. But some of these values are, very, very small, as you can see over here, just like to the minus 48, just looking at it, this is to the minus 28, so for all intents purposes, there's a lot of things that are pretty much considered completely insoluble. But again, if you sort of do the calculations and so forth, and in reality, even though it's almost all heading to the reactant side where you have your solid, it's still an equilibrium that gets set up, which means even though it's mainly all on the reactant side, there's still going to be a little bit of it that's going to find its way to the product side and sort of break apart. And again, this may be something obviously that's very, very small. Here's some more values in case you need it. So when we do sort of KSP type problems, there's really sort of two problems that we oftentimes will sort of work through. And there's usually sort of two sort of solubility things that we look for or try to solve. The first one is what is sometimes referred to as obviously the molar solubility. And that is a fancy way of just really saying what is the molarity, basically. So again, our molarity, which is our moles per liter, is again the number of moles of solute that's dissolved in 1 liter of a saturated solution. So sometimes in these problems, they will want to know what is basically the molarity or the molar solubility. And then sometimes they'll want to know maybe a more useful sort of number, which sometimes is just referred to as the solubility in grams per liter. And that would be obviously how many grams you could dissolve in a liter of solution. Now, there's really sort of two types of these problems, and it is really based on sort of the information that's given to you in these problems. The first type of problem is the top one here, where the ultimate goal is to actually calculate the KSP of a solution. And usually in that case, they will give you the solubility of the compound. So they'll usually give you the molar solubility. And then you need to figure out the molar solubility. You need to figure out the concentration of the ions, the positive guys concentration, the negative guys concentration. And then you essentially could put it into this expression, your positive guy and your negative ion. Again, your products would be pretty much these guys. Your reactants would be solids. And by figuring out those concentrations, you basically can kind of plug and chug it into here. In that type of problem, when you're given the solubility of a compound and you want to figure out the KSP, as we will see in just a second, you don't necessarily have to do an ice table. You could do an ice table to sort of help you understand, sort of what's happening in terms of those ions. It will also maybe help you understand how to get to the concentration of each of the guys. So in that type of problem, like we just described there, an ice table is not necessarily necessary. But in the second type of problem where they only give you the KSP, and you're trying to figure out the solubility of a guy either in grams per liter or molarity, in this type of sort of situation, you do usually have to do an ice table. So, the top problem, you don't necessarily have to do an ice table. And we'll do an example in just a second where I'll show it to you sort of both ways and show you, again, why you don't necessarily have to do an ice table, but you could if it kind of helps you visualize it. But definitely, if you're only given the KSP value, you would do an ice table to basically figure out the concentrations of everybody at equilibrium, and then you'll be able to figure out the solubility of that product. So the calculation here is slightly similar to a traditional ice table like we've done already a number of times with equilibrium problems, with acid-base problems. Again, there's just going to be a slight few different things that we typically will do here that maybe we don't do necessarily in other ones, but it's very similar. So let's take a look, for example, I think at the next one, and we'll go through it together just to kind of give you an idea of what I'm talking about here, where you maybe don't need to do an ice table, or you could do an ice table. So let's take a look at that one here. Thank you. So if we have this problem, and this is a problem where we're looking to figure out the KSP for silver phosphate, and in this case, we are given silver phosphate, the solubility of it as 1.6 times 10 to the minus 5 moles per liter, and we want to know the KSP value for it. So in this problem, like I mentioned before, when you are trying to find the KSP value, you don't necessarily have to do an ice table. But what I'm going to do is show you what the ice table will look like, because again, it is slightly different than how we normally do ice tables. Not extremely different, but a little bit different. And then again, after we're done with it, I will show you how you could just go do it without the ice table. And but what I'm going to show you here is the sort of the method that you can use for problems where you definitely do need to do an ice table. So the first thing when we want to look at this is we want to set up our sort of equation, and it is just going to be our silver phosphate here. And our silver phosphate, by the way, we know it's a solid because we're looking for a KSP value, and it is going to set up an equilibrium, and it's going to break apart into 3 silvers plus a phosphate. Yeah. And again, here we're looking for the KSP value. Any questions on how to break that up? So that's also really important when we go to break this up. So once we have it broken up and we're actually looking for the KSP value, we could also write our KSP expression for this, which would be our KSP would equal our products, which would be the silver ion. And again, we would have to cube it, which is why it's important to make sure you break it apart correctly, times the phosphate here. And again, that would equal the KSP value, which is what we're looking for. All right, so I'm going to show you how we can do this table here. All right, so when we do an ice table in a problem that involves KSP, we can do it like normal. So like normal, since this is a solid, it essentially is not going to be used here, right? Because it's not going to really participate in anything. So we can, again, pretty much ignore it for the time being. We, again, don't want to maybe put numbers there or anything like that where we might be tempted to use numbers. So traditionally, what we're going to assume here is we're starting with 0 of each of these guys. Now, when we do a KSP ice table, normally the change part, we use X. And truthfully, you could still use X in this table, but a lot of people will not use X in this table. A lot of people will actually use S. And what the S will stand for is the molar solubility. And truthfully, if you still like X, you can use X. And heck, you could use any letter you like, I suppose. But traditionally, when people do sort of these sort of ice tables that involve KSP problems, they do use this S. And the S will work the exact same way as the X that we've done previously in tables, We still want to take the coefficient into account. So we're still going to assume the reaction is technically going this way, which means this would be plus 3s, and this would be plus s again for the coefficients that we have there, which means when we come down, we technically would have 3s and s. Any questions on sort of what an ice table looks like and sort of a KSP problem? Okay. Now, normally what we would do, right, in an ice table is we would take our equilibrium and we would put it into our KSP expression, which we could still do here. And that would give us 3s, and you still need a cubit times s, right? Now, if we were actually trying to figure out what these solubility was, we would have the KSP value. But in this case, we're actually trying to find out what the KSP value is. Now, this is where the other piece of information from the problem is important. It says the solubility of silver phosphate is 1.6 times 10 to the minus 5, and that's basically molar. That is really the molar solubility. And in our table, that is really what S equals. So what we could do at this point is go 3 times 1.6 times 10 to the minus 5. Again, you don't want to hit the button like that. There you go, come back. And then we would again make sure that you cube it times 1.6 times 10 to the minus 5. Now, when we do all that good math, maybe 1.6 to the minus 5, do a little cubage action, times it by 1.6 to the minus 5, gets us something like 1.8 to the minus 18. Again, this is a K value, which means we don't need units. So that's why we didn't worry too much about the units here. And we do get our KSP value for this, which is 1.8 times 10 to the minus 18. That obviously is a very small value of K, which means essentially, like we've been talking about, that pretty much this is what you got going on in that solution. You pretty much have mostly solid, but there is just a little bit of it kind of coming apart at the in the solution. First off, any questions on sort of the ice table? So again, the ice table here is not really necessarily per se in this type of problem, and I'll show you in just a second why that is. But I would say, even in this type of problem, it is sometimes very helpful to do the ice table, because very common people are like, all right, I'm technically multiplying by 3. Do I still need to cube it as well? And they get all that sort of confused. Like, I multiplied by 3. Oh, I don't need to cube it now. Or I cubed it. I didn't multiply by 3. So sometimes doing the ice table, even in a problem like this, is helpful because you can kind of visually see sort of what you need to do. Now, when I say you don't necessarily have to do the ice table with this, and it's because if you understand concentrations and how they relate when something breaks apart, you pretty much can figure it out by kind of doing the ice table without doing it. So when we do have something like this, if we know the concentration of this whole thing, which is essentially what we did know in the problem, and the relationship is it's a 1 to 3 relationship in terms of the silver, you basically just take 1 times 6 times 10 to the minus 5, and that would give you the concentration for the silver. It's a 1 to 1 relationship with our phosphate, which means this guy is going to be 1 times 10 to the minus 5. And that's essentially what we did here with the ice table. But if you understand that relationship right off the bat, you can just slap those numbers right into that KSP expression, and you will get the same answer. So again, if you understand that if you take basically something breaks apart into a 1 to 2 relationship, you take the concentration, multiply it by 2, and then put it into the expression, you're good to go. And again, that's essentially what the ice table is doing for you, but in a little bit more of a organized fashion that you won't perhaps miss the part, because again, very common people will miss this part and just go in with the 1.6 times 10 to the minus 5 and just cube it. Or people will do this part by multiplying by 3 and forget to do the cubing part. So again, sometimes this ice table kind of puts it together a little bit more straightforward than just taking the concentration and sticking them in. But again, if you clearly understand how the ion's concentration relates to the whole thing, you can basically just figure out the concentration of each of the ions and technically stick it in without technically doing the formal ice table. So you could do the ice table like we did on the left there, and it kind of helps organize everything, make sure that you multiply and kind of square or whatever you need to do correctly. Or again, kind of the bottom right there, you can kind of quickly just figure out the concentrations of each ions and go right into the expression. Mathematically, it really is kind of the same thing. It's just, one you can maybe do a little quicker than the other. But again, there will be problems when you're given the KSP, and that's the only thing you're given where you do have to do the ice table, really. And you should do the ice table. Any questions on how to solve that type of problem? Okay, and again, if you do have questions, feel free to type them. And why don't we look at another one here, and why don't you give it a go? So we're looking for the solubility of silver chloride in grams per liter, and take a minute or two, a couple minutes, and work through it. I'll give you the molar mass of each of those things in just a second. All right, so let us take a look at this. So in this particular problem, we're just given the KSP, and this is typically the case where you do want to do an ice table. So really all these ice tables are really just going to be based off of the solid. And again, we're given the KSP, so we do know, even if we don't know solubility rules, that this is probably a solid. So our silver chloride is going to break apart into a silver ion plus a chloride ion. Our KSP expression would be, in this case, again, our products, which is our silver times our chloride. And that's going to equal 1.6 times 10 to the minus 10. So again, we're going to do an ice table, and because the solid here, nothing's going to be put there, we're going to assume 0 and 0 to start with. Our change will be plus S and plus S, which means when we do reach equilibrium, we will get S and S. So very similar ice table like we've done in the past. And in this case, like we've done in the past, we then want to put our equilibrium values into our expression and basically solve, in this case, for S. So if we do that, we got our KSP would equal basically S squared. And that's putting the S into here and the other S into here. And that would equal 1.6 times 10 to the minus 10. We're going to take the square root of both sides, and that will give us an S of 1.3 times 10 to the minus 5. And remember that S does equal the molar solubility, which means technically that would be the molarity of the silver chloride. Now you may say, isn't that S? And it is S, so that is the molarity of the silver ions at equilibrium. That's also the molarity of the chloride ions at equilibrium. And if we do sort of our stoichiometry going backwards from either one of those, it's a 1-to-1 relationship between the silver ion, for example, and the chloride, which means that this guy technically would also equal S at the end. So that's how we can could get it to the whole thing. And because typically when you do a nice table and all this good stuff, you take that coefficient into account. Pretty much when you solve for S in these tables, that is, the solubility of the entire thing, basically, say the silver chloride in this case. Um, it may not necessarily be the solubility of the ion, because it may have like a 2 in front of it or something like that. But if you do it, relate it back to the entire solid, it will be the solubility of it. Now, that's only the molarity of silver chloride. So that technically is 1.3 times 10 to the minus 5 moles per liter of silver chloride. But we're looking for the solubility here in grams per liter. So really, we need to convert from moles to grams. And again, we need the periodic table and the molar mass to do that. And if we add up that molar mass there, we got 107.9 plus 35.45 gets you about 143.4 grams per mole. So we would actually multiply by the molar mass of 143.4 grams per mole of silver chloride. The moles are going to cancel, and that's going to leave us grams per liter. And if we do that, we get something like 1.8 times 10 to the minus 3 grams per liter of silver chloride is soluble in water. And just to put that into a sort of a decimal, that's 0.0018 grams per liter. That is not very much, right? So you basically can dissolve in 1 liter or 1,000 milliliters 0.0018 grams of silver chloride in water. And as you will know, that is a very small amount, which is why we typically will consider silver chloride to be solid. Actually, I probably should round that to 9. Looking at my calculator. Change that real quick. Looks like maybe 9 would be a better number there. There we go. So that's an extremely small amount. Again, in 1,000 milliliters, you can't even dissolve 0.1 grams. You got to see if you get 0.00, basically 2 grams. And it's a very, very small amount, which is why when we think about silver chloride, we think about it being pretty much insoluble, because obviously that is not a lot that's going to dissolve. Any questions on that? So why don't you try this next one here? Calculate the concentration of aluminum in a saturated solution of aluminum hydroxide. The KSP is 2 times 10 to the minus 32. So see what you come up with on this one. We'll talk about it in a minute or two. All right, so let's take a look at this one. So again, this is a problem where we're just given the KSP, so we should do an ice table. And again, if you're not sure about solubility rules, because you are given a KSP, it's a pretty safe assumption that this is going to be a solid in that case. And again, we want to make sure we break it apart into the proper ones. So that's going to give us an aluminum ion that has a +3 charge. It's going to give us 3 of these hydroxide ions. And obviously the KSP in this case will equal 2 times 10 to the minus 32. Our KSP expression is going to be our product. So that's going to be the aluminum times our hydroxide. Again, here we want to make sure that we do cube it because of the coefficient that we see here in the equation. So initially here, again, we're going to ignore our reactant side, which has our solid. We're going to zero out our product side there. Our change is going to be plus S. And again, important here, plus 3S. So this is going to make sure we multiply it by 3. Again, 1S over here because of the coefficient. That is going to get us to our equilibrium here, which is going to be S and 3S. Any questions on the ice table there? So again, very much like a traditional sort of ice table, you want to make sure the important part here, like usual, is those coefficients and obviously the cubing of your KSP expression in this case. And that's important because now we're going to take out those guys and put it into our expression. So our aluminum equals S and our hydroxide equals 3S. And again, where people always forget, you got to still make sure again that you cube it. And that's going to equal our 2 times 10 to the minus 32 in that case. That is going to get us a number. That is going to get us 27 S to the 4th equals 2 times 10 to the minus 32. I will say as well, the other thing that people screw up on is they decide, I will always cube that guy, but they kind of forget to do the number, yeah? So remember, you got to do the 3 times 3 times 3, yes, which gets you the 27. So it's very, very common mistake that people make is they, for some reason, will always sort of square the S or cube the S, but for some reason, they always like to leave the number alone. So make sure that you do actually apply, in this case, the cubing to not just the S, but also the number. That means we're going to divide 2 times 10 to the minus 32 by a 27. And that will get us a S to the 4th equals 7.407. I'll take it a couple of digits, minus 34. We want to take the 4th root of that, right? And if you take the 4th root on your calculator and hopefully do it correctly, you get a final number here of 5.2 times 10 to the minus 9. And just to talk about this little part here. Now, some people on their calculators do have a button that is like this, which obviously you can use. If you don't have that button or not sure how to sort of properly use that button, you could take the number like we had, 7.407 times 10 to the minus 34. You could hit your caret button, open a parentheses and do 1 divided by 4. And that will do your 4th root for you. Or you could do 1 divided by 2. Technically, it would do your square root. 1 divided by 3 would do your cube root, and so forth. So you can do, again, that 10 and a caret, that caret, parentheses, 1 divided by whatever the root you're going to do if you're not sure how to punch that into your calculator sort of properly. Questions on that? So to sort of answer the question, though, here, just so everybody is clear, the aluminum concentration, if we look at the table, does equal S, which means its concentration should be 5.2 times 10 to the minus 9 molar, or really probably should cut it to 1 sig fig since that's the only number we have, but we'll leave it like that for now. Our hydroxide, though, which wasn't asked for, we could also figure out our hydroxide concentration is actually 3 times S, which means it would be 3 times the 5, basically, times 10 to the minus 9. And we would have a hydroxide concentration in this case of 1.6 to the minus 8. again, wasn't asked for. But if we want to know the molar solubility of aluminum hydroxide, it would be this number here. It would be the 5.2 times 10 to the minus 9 would be the molar solubility of the whole thing. Any questions on that? By the way, when you do the fourth root on your calculator, you might have got a whole bunch of zeros and a 5 at the end, and it may just ran out of room. So if you put in scientific notation, that's where you'll get some more numbers. And sometimes you might need to kind of put some of these answers on your calculator, maybe into scientific notation. If you see your answers like slightly different than maybe a book answer or something like that, it's probably because they did it in scientific notation, so you'll get those extra digits. Sometimes if you have your calculator in decimal form, your calculator will run out of room and just kind of round that last digit. So on mine, for example, when I did it, I had all the zeros and it ended at 5 at the end. And it wasn't until I put it in, say, scientific notation that I got some other numbers and stuff like that. Question on that? So again, why I say the concentration of, or the solubility of the whole thing would be this number here is, for example, if we took this number, which was 1.6 times 10 to the minus 8 moles per liter of the hydroxide. If we did a stoichiometry problem between the hydroxide, which is 3 moles of hydroxide for every 1 mole of the whole thing, the moles of hydroxide would cancel, and we would be back to the 5.2 times 10 to the minus 9 moles per liter of the whole thing. So that's why when I said earlier that when you typically do solve for S, it is typically the molar solubility of the entire compound together, but it may not be the concentration of those ions or the molar solubility or concentration of those ions of the individual ions in solution. Like we see here for our hydroxide, you do have to multiply that number by 3 because you get 3 times as much hydroxide as you do aluminum in this case. So when you solve for S, it is the molar solubility of the entire compound together, like aluminum hydroxide, but individually when those ions break apart, they do have a different concentration in solution. Any questions on that? They're both extremely small, but we have more hydroxide in that solution because when it breaks apart, you get 3 to 1 basically, right? So you get 3 hydroxide ions for every 1 aluminum in this example, which is why when we compare just these 2 concentrations, the aluminum and the hydroxide is more concentrated because, again, it's a 3 to 1 situation when it breaks apart. Any questions on any part of that calculation? So this is just a table, not from your book, but I think you have a similar table, but it just sort of gives you the different, if you want to kind of break it down mathematically, the different sort of ways that you would mathematically do these things. Like you're going to take 4s cubed when you have basically 2 and 1 in terms of the ions. You'll get 27s4 like we just saw with our aluminum hydroxide. So there are some patterns that you commonly will see based on how many ions basically break apart. Now, we can use KSP values in certain situations to help us decide what salt, for example, what ionic compound would be more soluble and which one would be perhaps less soluble. And in certain situations, we can actually use the KSP value directly to make that judgment. So again, if we just think about KSP and sort of how it's set up, those equations, again, are always solids on the reactant, ions on, aqueous ions on the right-hand side. So when we think about our KSP value, again, a smaller value would mean that we would have more solid. Again, a larger value would mean we would have more products, right? So we can compare the KSP values for salts, and there's an important sort of rule that you have to follow if you want to do that. And the rule is you can only use the KSP values with salts that break apart into the same number of ions. So what does that mean? So we take these three guys right here. When silver iodide breaks apart, it breaks apart into a silver ion and an iodide ion. When copper 1 iodide breaks apart, it breaks apart into a copper ion and an iodide ion. And when calcium sulfate breaks apart, it breaks apart into a calcium ion and a sulfate ion. So what we mean by the same number of ions is pretty simple. We get 1 silver, 1 iodide. That is the grand total of 2 ions it breaks apart into. 1 copper ion, 1 iodide ion. That is 2 total ions. 1 calcium, 1 sulfate. That's also 2 ions. So the only time where you can go to a KSP table and take the KSP values and compare a number of different sort of salts is when they break apart into the exact same number of ions. So in this case, we could compare the KSP values for silver iodide, copper 1 iodide, and calcium sulfate because each of those guys will break apart into 2 total ions. And because they break apart into 2 total ions, we can directly use the KSP values to compare them. And if we did look up on that table, what we would find is the calcium sulfate is the most soluble of those three, and the silver iodide is the least soluble of those three. And that would mean that the silver iodide should have the smaller KSP value. I don't know off the top of my head, but if you look back on that table, this guy here should have the smaller KSP value. Smaller KSP value means that we would have more reactants and more solid, and thus be less soluble than our calcium sulfate, which would have the larger KSP value. Again, larger KSP value means we would have more products at equilibrium, and thus it would be more ions in solution and be more soluble. So you could go to a table, or if you're given KSP values, you could use that to determine which one would be more soluble, and that'll be helpful in some calculations we'll talk about later, where you can decide if I have these two guys in the solution, which one is going to precipitate out first and which one should precipitate out, second. And you could kind of figure out the order at which things should sort of precipitate out of solution, for example. Now, if you are trying to compare ions that do not break apart into the same number of ions. So if we look at this table here, this is copper 2 sulfide, breaks apart into a copper 2 and a sulfide ion. This is silver sulfide, breaks apart into 2 silver ions and a sulfide. This is bismuth, breaks apart into 2 of those and 3 of those. So this guy breaks apart into, in terms of number of ions, we got 2 for this guy, we got 3 for this guy, we got a lot of math there for that guy, that's fine. And if we went to the tables, these would be our KSP values that we would find for each of these. And if we did it just solely based on the KSP values, and we looked at the KSP values, what we would see is this is the largest, which would tell us that perhaps this guy should be the most soluble. And this guy is the smallest, which if you use KSP would tell you it is the least soluble. And the reason why you can't do that when we do break apart into different numbers of ions is if you actually calculated the solubility of these guys, like they did over here in this part of the table, what we actually see is the guy on top, the copper 2 sulfide, is actually the least soluble. And the guy at the bottom is actually the most soluble. And that is because of the stoichiometry and how it breaks apart into ions. You have to take that into account. And that's not taken into account if you just strictly go on the KSP sort of values. So what that means is if you're comparing two salts that do not break apart into the same number of ions, you cannot, so let's put a big X over it, you cannot use the KSP values from the table to figure out which one would be more soluble. You actually have to do the calculation here. So you'll have to do like an ice table, right? And you'll have to do the ice table calculation to actually calculate it. So the one sort of limited place where you can sort of use the KSP values from the table directly to figure out solubility is only in a case where you're comparing 2, 3 things, whatever main things, that break apart into the same number of ions. So like in the previous example, everybody broke apart into 2 total ions, and then you can use the values. Otherwise, if you're comparing things like in this table, one breaks apart into 2 ions, one's 5 ions, 3 ions, you actually have to sort of physically do the calculation to figure out the solubility. Any questions on that? So earlier I was talking about the idea that sometimes when we think about solubility rules, we oftentimes think of them as definite for sure. That, no matter what happens, hey, my trusty solubility table that I never learned, I got it hiding somewhere, tells me that this thing should be insoluble and should make a solid. And 100% of the time, in every single situation that occurs, I would expect this guy to make a solid. And again, that's not always going to be the case when we talk about solubility. So one thing that affects solubility, the first thing we're going to talk about that sort of affects the solubility of salts, for example, is something that we talked about when we talked about buffers. So if you remember in buffers, we had the idea of what is known as the common ion effect. And the common ion effect is basically just like in a buffer, the presence of a common ion. And the presence of a common ion will have a big effect on the solubility. And again, if we just think about it, it's very simply, as we've been talking about, all these reactions, solid on the left-hand side, ions on the right-hand side, which is our aqueous, right? And again, these are going to be our ions. So if we have a common ion in a sort of solution, that means that we are essentially adding to our product side. And our good friend Le Chatelier's principle will tell us that is going to cause the equilibrium to shift away and shift to the left in this case, which means when it starts to shift to the left, we will be making more solid. More solid means that we have just decreased the solubility, right? More of that salt is going to stay together because of this common ion that's present. So to illustrate this, let's take a look at this example here, which is what is the molar solubility of silver bromide in pure water? And then we're going to look at the molar solubility of silver bromide in a solution of sodium bromide. So I tell you what, why don't you take a minute or two and do just part A, which is what is the solubility of silver bromide in water? And the KSP value for silver bromide is that number there, the 7.7 times 10 to the minus 13. So why don't you work on part A, then we'll talk about it, and then we'll talk about part B. Okay, so let's take a look at part A. So in part A, we're just going to do a basic sort of table like we've done before. We have the KSP here for silver bromide. So we'll start with our silver bromide here. Again, we're given the KSP, so even if you're not sure about solubility rules, pretty safe bet it is a solid. Going to break apart into a silver ion and a bromide ion. Our KSP expression here would be the silver ion times the bromide. And that equals 7.7 times 10 to the minus 13. Again, this is a case where we're just given the KSP value, so we should do a nice table. That's going to be 0 and 0. It's going to be plus S and plus S, which means at equilibrium, we have S and S. That essentially means that we will put that into our KSP expression, and that should give us S squared equals 7.7 times 10 to the minus 13. And if I do that, take the square root, 7.7 to the minus 13, we end up with a number of, we'll call it 8.8 to the minus 7. And again, that would be the molar solubility in this case. And that means that the molar solubility of silver bromide is 8.8 times 10 to the minus 7 moles per liter of our silver bromide. And again, if you want just sort of a more sort of visual reference of what that really means, if we multiply that by the molar mass of silver bromide, which the molar mass of silver bromide is about 187.8, we get a solubility in grams per liter of something here. Pretty good. There it is. We get something like, what did I just say that was there? 187.8. So this would be 187.8 grams per mole for silver bromide, and gets us something like 0.00016 grams per liter, which is not very much for silver bromide, right? So this would be our molar solubility in pure water. So in pure water, starting off, not a lot happening in terms of it being able to dissolve. Any questions on that? So it just asks for the molar solubility. So the answer to part A would be obviously this number here. This technically would be the answer here to part A. Any questions on that there? So let's talk about part B. So now we're going to take the same sort of silver bromide, and we're not going to just put it in pure water, but we're going to put it in some water, for example, that has some sodium bromide in it. And when we have something like sodium bromide, it is a soluble ion compound. And when silver bromide goes into solution, it is going to produce silver ions and bromide ions, right? And when we look at our original sort of expression here, the common ion in the case of the silver bromide is going to be the bromide ions that are going to be supplied by the sodium bromide. So we can figure out the concentration of the bromide ions in that case, because this is 0.001. It's a 1-to-1 relationship in terms of the whole thing to just the bromide, which means this guy would be 0.001. And we would do our ice table the same way. So we'd take our silver bromide, which is the thing that's going to set up the equilibrium because it has the KSP. And much like a buffer, if you choose to do an ice table, which you do have to do in this case, But when we talked about buffers and doing ice tables, it's important not to just randomly zero out both of these. So if you zero out both of these guys to start with, you essentially are going to be doing the exact same problem we just did. Because in this particular case, the concentration of Br minus is not going to be zero, because this sodium bromide is going to supply a certain amount of bromide, which was 0.001 to begin with. So this is a slight difference in how we do this problem. We do have an initial concentration of that common ion. The rest of the table will be similar. So the change would be plus S and plus S. At equilibrium, we would have S and 0.001 plus S. Just like we did on the left-hand side here, we're going to put that into our KSP expression, and that's going to give us S times 0.001 plus S equals our KSP value, which is still the same, of 7.7 to the minus 13. Any questions so far on this table? Now, just like we've done previously, we sometimes want to make the calculation a little bit easier. And we can make an assumption here, just like we did previous. And we can assume in this case that S is equal to 0. We can definitely do it in this case because when we look at our K value, which happens to be our KSP value, it is 7.7 times 10 to the minus 13. That is a super small value, which means that we would expect when we do reach equilibrium that, we're pretty much going to have this guy there mainly. And what that means is if it's not going to break apart a lot, we would not expect the change, or the S part in this case, to be very different. Just like what we do it with X's, and we assume that X is equal to 0, you obviously cannot cancel out all the S's. Otherwise, you have nothing to solve for. So just like before, in this case, you're going to get rid of the S's that you are plusing something from. So that would be, in this case, this S. So we're going to assume that S is equal to 0. That essentially gives us S times 0.001 equals 7.7 times 10 to the minus 13. We're going to divide the other side by 0.001, and that will get us 7.7 to the minus 13 divided by 0.001. Gets us an S value, over here, of 7.7 times 10 to the minus 10 molar. Right? We can check it like normal, so we could take it divided by 0.001, times it by 100, and you should check it probably, but I'll be honest with you, in most cases, you're probably good to go here on the solubility type problems because the KSP value is so small. But never hurts to check just in case you get like a weird one maybe. But usually I would say probably 99% of the time, you're probably okay. And what we want to look at is we see if we just compared the molar solubility, and if we wanted to convert that into grams per liter, again, just to kind of compare it, we would take that and times it by the 187.8 from the periodic table. And that tells us that we can dissolve, again, if you times this by the 187.8, 0.123456, I think. 1, 2, 3, 4, 5, 6, 15 grams per liter. So what we do see, just looking at the molar solubility, which is what this question asks for, in pure water, the solubility of silver bromide in terms of this molar solubility, 8.8 times 10 to the minus 7. In sodium bromide, where we did have the common ion, the solubility dropped a lot to 7.7 times 10 to the minus 10 molar. it is definitely less soluble here in the sodium bromide, because when we have that common ion like we did here, it is going to cause this equilibrium to shift to the left and thus keep the salt together and not break apart as much. Any questions on that? So one effect on solubility, as you can see, is the presence of that common ion. And it will, again, suppress basically the salt from breaking apart and decrease the solubility. So why don't you try this one here and see what you come up with. What would be the solubility of silver chromate in a solution that is 0.1 molar? If you want, you could do the molar solubility here. It's good. Actually, let's do both just to see. Do the molar solubility. And do the solubility in grams per liter. I'll give you some numbers here that will be helpful. Silver, 107.9. Cr, 52. And oxygen, 16. All right, so calculate the molar solubility and solubility in grams per liter of this guy in a presence of 0.1 molar potassium chromate and see what you come up with. We'll talk about it in a couple of minutes. Okay, so let us take a look here. So we want to know, we have the KSP value for our silver chromate. And again, that gives you a pretty strong indication that that's going to be a solid because it has a KSP value associated with it. Again, typically KSP values are associated with things that are kind of insoluble. Um, we want to know what is the solubility of the compound if it's already in a solution that contains potassium chromate. So if we take our silver chromate, it is going to break apart. And again, we want to make sure we get the right way it breaks apart. So you should get 2 silvers and you should get 1 chromate, which is -2. Our KSP expression in this case would then be the silver ion, which we do need to square because of the coefficient, times the concentration of the chromate here. And again, that would equal our 9 times 10 to the -12. Now, the additional thing is we do have it in a solution that contains potassium chromate, and potassium chromate looks like this. And potassium is soluble in everything, which means when this is in solution, it will break apart into a couple of potassiums and a chromate. And in terms of our sort of equilibrium that's set up, it is going to be the chromate that's the important one there because that's going to be our common ion, right? So again, if you understand molarity, if the whole thing is 0.1, it again breaks apart into a 1-to-1 relationship with the chromate, which means the concentration of the chromate would be 0.1. By the way, the concentration of the potassium, which you don't need in this problem, would be 0.2. Again, a 1-to-2 relationship here. So you multiply the molarity by 2. So really what this affects, again, is the initial part of our ice table. This is going to be 0. But again, we actually do have some concentration of the chromate in the solution provided us by the potassium chromate. The rest of the table here going to be just like normal. We want to make sure that we also do a 2s here because of the coefficient and an s here. We want to then carry everybody down. So that's 2s, 0.1 plus s. Any question on the table? Okay, so, and again, if you do have questions, make sure you do ask, but we are then going to pop that into our KSP expression. So our KSP in this case would equal our product. So this is going to be 2s. Again, we need to square it here because of the 2 that we see here. And that's going to be times 0.1 plus s. And that's going to equal 9 times 10 to the -12. Again, on these KSPs, pretty good idea to assume that s is equal to 0 in this sort of situation. Again, only going to be the s we're adding, so we're going to get rid of that s. That will then leave us 2s squared times 0.1 equals 9.0 times 10 to the -12. Going to do a little bit of math there. So again, you want to make sure that you square the number in addition to the s so you don't miss it. And that will get us 0.4 s squared equals 9 times 10 to the -12. We're going to divide both sides by the 0.4. We're also going to take a square root of it as well. And when it's all said and done here, looks like we end up with an S, if I did all the math there, 4.7 times 10 to the -6 molar. And again, this would be our molar solubility. Again, it would be our molar solubility for this guy, would not be the solubility or concentration of our ions, because we would have to technically for silver take 2 times it to get the right concentration. And we would need to take our chromate over here and figure out its concentration by popping that in there as well. So in this case, we also wanted it in grams per liter, so we could use the molar mass to do that. And the molar mass of silver chromate is 107.9 plus a 52 plus a 16 times 4, something like 223.9, I think. I think I missed the number there. I'm going to try that again. Hang on a sec. 107.9 plus another 107.9 would be good. Plus 52 plus 4 times 16. I think I missed that second silver. I did. So it actually is, good thing they still have erasers on here. It actually should be more like 331.8. Grams per mole times our 4.7 to the minus 6 gets us something like 1.6 times 10 to the minus 3 grams per liter would be the solubility of this guy in that solution. Any questions on common ion effect and solubility? So the overall take-home message here again is that the solubility is definitely affected by that presence of the common ion. It is really the basic Le Chatelier's principle happening there, where that common ion is going to shift the equilibrium to the left and really suppress that guy from dissolving and keep it together. Any questions so far? Okay. So for lecture, we're going to stop here today. Let's talk about a couple things that's on tap. Make sure everybody's on the same page. First off, we will continue lecturing on Tuesday on this, and we should probably finish the chapter on Tuesday. The next exam was actually scheduled for the 7th. So the exam will be moved to the 12th. That will give you, that should give you kind of a week to study for it. So exam number 2 will be on Tuesday, May 12th. It will cover chapter 14 and the one we're currently in, which is chapter 15, and is usually sort of the hardest exam for a lot of people because it covers the buffers, the titrations, this stuff here, the KF, which we'll talk about on Tuesday. So that's the first thing. So exam number 2 will be, let's see if I have another page. I do. We'll do it here. So exam 2 will be May, where did it just go? 12th, I think I just said. Yep, 12th. Again, chapter 14 and 15. Yeah, so for the proposal, which is the next thing I'm going to talk about, there actually is up on Canvas, there's an assignment for the proposal. It should be right underneath where the updated project PDF is. So in the module section, you'll find the updated projects PDF. There's also like an assignment little there where you can upload your proposal. I did extend it, I think, until Sunday, as some people were asking earlier today, just to give you a few extra days to kind of put it together. So I think it's now officially due on the 3rd, which I think is the end Sunday. So try to get it in there. You can do it now if you want. It's been up there for a while, I think, the assignment thing. But you'll find it in the module section right underneath the PDF for the revised project. So that you do want to get in. Again, proposal wise, nothing super long or anything like that. As we talked about before, basically you just need to have your two sort of topics, a little bit about the two topics and how it relates to the course. Obviously, topics, the class and the course topics we talk about. Obviously, who you're going to be working with virtually, if you are working with somebody virtually, and you can submit that. Like I mentioned, I think as well, if you want, since you will be working with somebody or multiple people, you could just submit one proposal per group if you like, if you trust somebody, or you each can submit it if you want, but do make sure that you put on there obviously who you're working with, so I have an understanding of that. And again, just the basic two topics, a little bit about them, and again a little bit how it ties to the class, and that should be good enough for here. So nothing super long or anything like that. As you can see, I have a ton of stuff to grade still, so nothing super long, just enough information for me to look at it. So you have until Sunday to kind of submit that. I'll take a look at it after Sunday, and hopefully sometime next week I'll get back to you, and I'll send it back to you, or kind of mock it up and kind of approve it, and then obviously continue on working virtually with the people that you need. I think on Canvas as well, there's places where you can kind of conference with each other maybe, or kind of use that to kind of talk to each other and virtually kind of get together. You do have a lab that is, I think, due officially today, which is the pH and hydrolysis experiment. For this lab and the next one as well, just so you know, there is a due date. You should obviously get it in by the due date. But just in case something happens, you don't need to email me. You can, I think, still submit your lab after the due date. I think it's sort of set up that way. And what that means is it'll just be marked late, and I'll look at it and obviously make the decision when I grade them as to how late is. Yes, so there will come a point where you will be too late and you'll lose points, but if it's maybe just slightly, you missed it by a little bit, you probably will be okay. So and for this one that's due today, the pH one and the buffer one, I think they're both set up that way, so you don't have to officially email me and ask if you could turn it in late. If you needed to for some reason that occurred, you can kind of upload it. I think after the due date, it will be marked late. And if you want to then email me and let me know why it was late, and I'll take it into consideration. Obviously, try not to make it late. Try to get it in on the time that it's due. But just so you don't have to feel like and wait for me to say, hey, it's okay for you to upload it, I think it's set up in a way where it will still take it even after the due date, but it will mark it late. And then obviously, like I said, depending on your lateness, hopefully there's not a lot of that, I will take into consideration the appropriate amount of points or something that might have to be deducted. Hopefully, if it's not too late, it'll probably be okay. Any questions on that? So in terms of labs that you should be working on, hopefully you have that one pretty much done. If not, you probably should start cranking out on that pH and hydrolysis experiment. You also should be working now on the buffer experiment, which again, was open at the beginning of the week here, and we did talk about it on Tuesday during lab, so you can work through that as well. Officially, we will start then the titration experiment on Tuesday coming up, and that will be due a little bit down the road, but we'll officially start that one as well. And that should keep us semi on track in terms of our schedule and everything like that. Any questions on any of that stuff? That obviously means the textbook homework, obviously for exam 2, will be moved to the same day as the exam. So that will be May 12th when that will be due as well. And like I said, I apologize. I have a lot of stuff to kind of grade and stuff. So I am going to try to get through some of those labs and stuff like that and start trying to grade some of that stuff. That's sort of my goal. Hopefully this weekend is to get through some of that. It's just, I've had a lot of online exams these last weeks and stuff. So I'm going to try to catch up on some of that stuff. Any questions on any of that? So for lab today, since again, we ran a little bit long here, I'll start lab maybe at 12. So we'll take like a half-hour break, gives yourself a little time to stretch. And like I said, I'll be there. I'm not going to lecture or anything during lab today. I'll just be there to answer any questions that you may have, obviously on the pH one, in case you still happen to be working on that, and the buffer experiment as well. So remember the buffer experiment, there is a couple of parts where you technically has to get your calculations sort of approved for it to unlock the next part of the experiment for you to kind of do the simulation. So make sure that you again submit those things. I think I put a little message online on that. Make sure that you do submit those things with enough days left that I can have a chance to look at it and approve it, and then you could actually finish the experiment. So it's due, I think, next Friday maybe or something like that. So don't wait till next Friday to submit all those things. Otherwise, again, you may run out of time to finish the experiment. So try to stay on top of that. And obviously, if you have questions, make sure that you do ask. In terms of that, I did email everybody, I think individually. Hopefully you saw it. I emailed everybody through Canvas. I'm not sure where that goes. I assume it hopefully goes to your normal email. But if not, when you log into Canvas, there should be like a email inbox and stuff like that. So you could find your buffer assignments in that email. If you haven't got it in your regular email or you missed it, you should be able to find it there, or check for your regular email, because I did it on, I believe, Tuesday or Monday or Tuesday. And so everybody should have a specific buffer assignment of molarity and concentration that you're supposed to make for this experiment. So make sure that you do the one that you were emailed. And again, you probably can find it in your Canvas email, which I would assume would go to your regular email as well. But just in case you missed it, check it there. If you can't find it anywhere, let me know and I'll re-email it to you which one you were assigned. Any questions on anything that's happening, going on? Okay, so like I said, at 12 o'clock, I will open up the lab one. And again, I'm not going to lecture or anything like that. I'll sit here quietly, I guess. Now, I'm just kidding. If you do have questions, feel free to pop in and ask them, and I'll try to answer them for you. If you don't need that help, I guess, you're okay to officially during this time go work on the experiment like you would if you were in class. And other than that, if you're all good, again, make sure you come back through the lab link for the lab. Okay. Okay. I'll see everybody in a half hour if you have questions. Otherwise, have a good weekend. We'll see you next week if you're not going to pop back into lab to ask anything. And other than that, have a good one.